reminder, we are going to start section 1.3 today, and we're still finding limits, but it's not going to be by a table, it's not going to be from a graph, it's evaluating limits analytically. And this is important because you can't always evaluate a limit from a graph. You know, if you liked what we were doing yesterday, you might think, oh, I can just type it into my calculator, look at the graph, and do it that way. But a lot of times limits end up being kind of messy numbers, like maybe a fraction of some sort, and that is really hard to see from a graph. So what we do here in section 1.3 is going to be pretty helpful, evaluating limits analytically. Okay, and I'm going to start with a very important rule for not only today's lesson, but for pretty much all the other limit lessons that we have. The first thing to do in any limit problem is ... The first thing to do in any limit problem is, I feel like we need a drum roll here or something. This sounds really important. Plug in the value of x. Plug in the value of x that you're approaching and see if it works. That part might not make a whole lot of sense right now. How do I know if it works or not? We'll get to some examples that'll make that more clear. But we call this method direct substitution. And it's the easiest way to find a limit. So it needs to always be the first thing that you try. Unless it says you have to use a table or something like that. If it's specific about how to do it that way. But if you're just finding a limit in general, the first thing you should do is plug in the value of x that you're approaching and see if it works. All right, we'll run into some today that don't work using direct substitution, but this is, again, just always the first thing to do in any limit problem. All right, now I'm going to put up our directions for the bulk of the lesson, and it's just find the limit. I suppose we could add find the limit if it exists, but to be honest, I think they all exist today. I think we're going to get back something for every problem, so I don't think we'll have to worry too much about that. Okie doke. Number 1, we need to find the limit as x approaches 3 of x squared minus 3. The first thing to do in any limit problem is to plug in the value of x that you're approaching and see if it works. So let's try that. We're approaching 3. So let's take that 3, plug it in for x, so you don't really have to have parentheses around this. You can just take 3 squared minus 3, and this looks promising. That would be 9 minus 3, which is 6. It worked. So the limit as x approaches 3 of that function is 6. Okay, that right there is direct substitution. It's the easiest way to find the limit, so it's always the first thing that we try. Alrighty, let's keep moving here. Example 2, we got to find the limit as x approaches 5 of 2x over the square root of x plus 4. 2x over the square root of x plus 4. Well, Mrs. Street says first thing to do in any limit problem is to plug in the value of x that you're approaching and see if it works. So put a 5 right there. This is now, and on top, this is now going to say 2 times 5 all over the square root of 5 plus 4. Keep going. This is going to be a 10 on top. For the bottom part, square root of 9 is going to be 3. And you can't reduce that. I wouldn't even do a decimal here because it's not going to be a real nice one. So I would just leave that as 10/3. That would be hard to see on a graph. It would be hard to say from just a graph that you're approaching 10/3. So again, this is why we have other methods for finding limits. Okey-doke. I'm going to keep going here. Wouldn't be a good day in calculus without a trig function somewhere. Number 3, the limit as x approaches 3 pi over 4 of sine of 2x. X is approaching 3 pi over 4 and it's sine of 2x. Let's try direct substitution and see if it works. So wherever I see x over here, replace it with 3 pi over 4. Now I need to take 2 times 3 pi over 4. If you want to think of the 2 over 1, you could actually reduce this diagonal real quick. Divide by 2 on top and bottom. That's just a 1. That's a 2. So 1 times 3 pi is 3 pi, and 1 times 2 on bottom is just 2. Now, we could try this on a calculator. I'm not sure what we're going to get here. We would have to be in radian mode, so may want to check that first. 3 pi over 2, it does work out okay on your calculator. It gives you back a -1. Now, if you don't want to worry about the mode, or you type it in and you get back a really ugly decimal, don't use your calculator in those cases. Use handy dandy, the table at the bottom, because you want to always keep your answers in a good form. If it's some kind of a weird decimal, then it's probably some kind of a square root in your answer. So you want to leave it as a square root. Alrighty, let's keep moving here. Number 4, bless you. Number 4, it's the limit as x approaches 5 of cosecant of pi x over 6. Oh boy, cosecant of pi x over 6. Well, direct substitution, always got to try it first. Wherever I see x, plug in a 5. I'm not going to write pi 5 over 6. I'm going to turn that into 5 pi over 6. Now, if you wanted to type that into your calculator, anybody remember how to type in cosecant? Sine. 1 divided by sine. Cosecant and sine are reciprocals. So I guess you could type in 1 over sine of 5 pi over 6. But again, you know, that seems like a lot of work. You can also just use the table on handy dandy. Cosecant of 5 pi over 6 should give you a 2. Now I'm just curious, if I type this in, it had better turn into a 2. 1, oh good, it did. 1 divided by sine of 5 pi over 6. It would work on your calculator, but again, it's not always nice doing it that way, so feel free to use handy dandy. All right, well so far, direct substitution has worked pretty well for us. Every time we plug in the value of x, we've been able to simplify, get back something nice. Okay, so let's see what we get here on number 5. We need to find the limit as x approaches 3 of x minus 3 over over x squared minus 9. Here I go, direct substitution. Wherever I see x, I need to plug in a 3. That would be 3 minus 3 all over 3 squared minus 9. Well, 3 minus 3, that's 0. 3 squared is 9. 9 minus 9, that is also 0. Now, we actually have a kind of a fancy name for something like this. If you plug in your value of x and you get back a 0 on top and a 0 on bottom, we call that the, and I always make sure I spell this right, didn't do it right, better start over there, indeterminate, there we go, indeterminate form. It's the indeterminate form. It does not mean that the limit does not exist. That's very important. The indeterminate form means, and actually I think I wrote something down about this right here if you want to put it in your notes, it means that whatever you just did didn't work, but you might need to try something else to find the limit. It does not mean that the limit does not exist necessarily. It just means that you need to try something else. So if direct substitution doesn't work and you get the indeterminate form, try a different method. Don't give up. Don't give up. It just means that, again, direct substitution just didn't work. You gotta try something else. Okay, so here comes another method for finding limits. We've got finding limits by tables, by graphs, by direct substitution. That didn't work here though, so I'm gonna erase this since it didn't work. The next method on our list for finding limits is to find the limit by factoring. If you look at this function right here, x minus 3 can't be factored, but x squared minus 9 could be factored. That is a difference of squares. One of our special types of factoring, difference of squares. So I'm going to keep going. Now, you know, I'm not going to count off if you don't do this every time, but technically we haven't found the limit yet. So I left that notation out front because, again, I haven't really started to find the limit. I'm just trying to simplify my function, okay, and then maybe I'll be able to find the limit. So again, I left the limit as x approaches 3 out front. If you don't write that every time, I'm not going to count off, but technically it should still be there. Now, this is looking good because there's an x minus 3 on top, x minus 3 on bottom. Now it looks like there's nothing else on top, but what should we really put there? A 1. It's like taking x minus 3 divided by x minus 3. So anything divided by itself is still 1. And all I have on bottom now is just x plus 3. Once you get it factored and you get it simplified, now you can try direct substitution again. Take that value of x that you're approaching, plug it in, and cross your fingers because hopefully now it's going to work out to be something nice. And I think it does. If I put a 3 right here, 3 plus 3 is 6. So my limit is 1/6. Again, that would be hard to find on a graph to tell that you're approaching 1/6. So make sure that you know all of these other methods. Direct substitution comes first, but then if that doesn't work, factoring is just another option that you have. Alrighty, any questions on x approaches negative 2 of 2x squared plus 3x minus 2 all over x plus 2. Now I should always try to plug in the number first. Direct substitution, put that negative 2 everywhere you see x, and here's what happens. Negative 2 squared is 4. 4 times 2 is 8. 3 times negative 2 is negative 6. I still have another minus 2 after that. And on bottom, I would get negative 2 plus 2. But it happens again, a 0 on top, a 0 on bottom. It does not mean that we give up and we say that the limit does not exist. It just means that you need to try something else. Direct substitution doesn't work right off the bat with this problem. So now I start to search for something in this function that can be factored. And I'm looking at the part on top right here. Back in Algebra 2, I always called this yucky factoring because of the 2 in front of the x squared. If you need a little refresher here on how to factor with yucky factoring, let me show you real quick. To get 2x squared, we'll have to take 2x times x. Signs are different. I don't really know what is what yet. I'm just maybe going to put a plus there and a minus there and see what happens. And with yucky factoring, you're only looking for numbers that multiply to that last number. So the only numbers that multiply to 2 are 1 and 2, but I don't think I've got it yet. If I FOILed that out to check, that would actually give me a negative 3x in the middle. I needed positive 3x. So I just need to switch my signs. I'm going to make that minus 1 and then plus 2. That should fix everything that I need. Now, if you are paying attention to your function, if you see an x plus 2 on bottom, that's also kind of a giveaway there that probably one of these needs to be x plus 2, because what usually happens is you get something to cross out. Now, when you cross everything out on bottom, you don't really need to put a 1 on the bottom of a fraction. So I just made that 2x minus 1. And here we go again. Plug in the negative 2. So this is going to be negative 4 minus 1, which is negative 5. So limit as x approaches negative 2 is negative 5. Okie doke. Any questions on that one? Okay, I've got one more where we're finding the limit, I believe, and then after this, we'll talk about some limit properties. So this says the limit as x approaches 3 of x plus 3 over x squared plus 9. Now, I'm in the factoring mood because we've been factoring a lot on these problems lately, but nothing here can be factored, so I get a little concerned, but then I have to remind myself that the first rule in any limit problem is to plug in, I pointed at the 3 there instead of the x, plug in the value of x that you are approaching. So this is going to work. 3 plus 3 on top is going to give you a 6. This is going to end up being 9 plus 9 on bottom, which is 18. Divide by 6 on top and bottom, and that would be 1/3. So don't forget about direct substitution. You should always try that first no matter what. Okie doke. Any questions on that one? I'm going to keep moving here. Before I do number 8, I would like to go through these properties with you. They will be helpful, not only today, but later on when we keep learning more and more about limits. So there's a few of them here. I'm going to start with this. This is nice to know. The limit of a constant equals the constant. The limit of a constant equals the constant. If you were trying to find the limit as x approaches 1 of 4, the answer, I don't even care what I'm approaching, the answer is just going to be 4. Or if you were finding the limit as x approached 1 of 100, then the answer to that would just be 100. The reason is, I'm going to go back to the smaller number real quick. The reason is, if you think about 4 as a function, like f of x equals 4, that is a horizontal line, 1, 2, 3, 4, a horizontal line at y equals 4. So imagine approaching any x value on this line. If I'm trying to approach the x value of 1 from both sides, what y value am I approaching? 4. Or if I tried to approach negative 2 from both sides, doesn't matter what x value you're approaching, you're going to be 4 the whole way through. It's just a constant function. Okay, so there's that. Something nice to remember. Now, next one, the limit of a sum equals the sum of their limits. The limit of a sum equals the sum of their limits. Okay, for that part, we're going to wait just a little bit. I'll have some examples in a minute where I can show you that a little bit better. But we can say the same thing about the limit of a difference, subtraction. The limit of a difference equals the difference of their limits. If you are finding the limit of 2x plus 3, you can find the limit of 2x and then just subtract from that the limit of 3. You can always kind of separate the limits. I'm going to keep going a little bit here. The limit of a product, sounds like we're just kind of repeating ourselves. The limit of a product equals the product of their limits. Okay. Now, before I do quotient, I'm going to save that one for the end. I want to talk about powers. This is another property of limits. We're going to use this one here in a little bit. The limit of a power equals the power of the limit. If you are taking the limit of x cubed, it's just the limit of x, the whole thing, to the third power. Now, finally, the quotient. This is the last property here. The limit of a quotient equals the quotient of their limits unless ... What do we always have to worry about in math when we talk about division? Yeah, dividing by 0. So the limit of a quotient equals the quotient of their limits unless that results in division by 0, then that's not going to be true. You can't do it that way. The limit of a quotient equals the quotient of their limits unless that results in division by 0. Okay, now I think you'll find the next few examples pretty easy once you kind of see how they work. And we are going to use these properties here. So the directions just say use the information to evaluate the limits. Use the information to evaluate the limits. It'll be a little bit different for each problem. Okie doke. And this is example 8. It's telling you what these two limits equal. It says the limit as x approaches c of f of x equals 6. We don't know what c is. We don't know what f of x is. All we know is that the limit is 6. And then the limit as x approaches c of g of x equals 3. Again, we don't know what c is. We don't even know what g is. All we know that is that its limit is 3. Okay, so let me show you part A here. Part A says we have to find the limit as x approaches c of f of x times g of x. Well, that's kind of hard to do on this problem because I don't know what f of x is, I don't know what g of x is, I don't even know what c is, but we do know a property about multiplication, and it says the limit of a product equals, I'm going to show you this next step right here. You could write this down too in your notes. The limit of a product equals the product of the limits. You can basically take the limit of each one of those functions separately and then just multiply those. Now, as you do more of these problems, you're not probably going to have to write this step out every time, but since we're just learning about these properties, I'm going to, because I want to show you how they work. The limit of a product equals the product of the limits. You can do the limits separately and then multiply. So look right here. What was the limit as x approached c of f of x? 6. So there's that. And then the limit as x approached c of g of x was 3. So all we have to really do here is take 6 times 3, and that's 18. Again, once you see how they work, they're pretty simple, and you're not probably going to show much work. But I do want to make sure you know how those properties are working. All right, well, let's try something else here. Part B, it's the limit as x approaches c of f of x cubed. The way it's written right now, f of x is the only thing that's being cubed. We don't know what f of x is though, so we can't work with that. But we do know the limit of a power equals the power of the limit. So we could take the entire limit as x approaches c of f of x, that entire limit, and we could take it to the third power. Okay, well, if you go back to the top, the limit as x approaches c of f of x is 6. So I just need to take 6 to the third power, and that will give me 216. That would be our answer then for part B. The limit of a power equals the power of the limit. Now, last one here. Again, these should be pretty simple ones to see how they work. Part C, we're finding the limit as x approaches c of f of x divided by g of x. The limit of a quotient equals the quotient of the limits. Looks a little weird up there, but it's like taking the limit of f of x divided by the limit of g of x. So put those in. Limit of f of x was 6. Limit of g of x was 3. 6 divided by 3 is 2. So that would be it for part C. Okey-doke. Any questions about properties of limits? All right. So this is our assignment here, C18, from page 84. We're doing 5 to 33 odd. Don't just copy the answers, check the answers in the back. I think it's helpful with these to know that you're doing them right. And then 37 to 41 odd, I'm guessing those are the property problems.